Today's talk through is a Cambridge IGCSE Physics Paper 4 Extended from June 22. A car of mass m is travelling along a straight horizontal road at a constant speed. At time t equals 0, the driver of the car sees an obstruction in the road ahead of the car and applies the brakes. The car does not begin to decelerate at t equals 0. Explain what is meant by deceleration. Remember, this is either a negative acceleration or a decrease in velocity of this car. And if we were to give an equation for deceleration, we'd say it is change in velocity over time. Suggest one reason why the car does not begin to decelerate at t equals 0. Mainly because humans take time to react, don't they? So we have to allow for their reaction time. Figure 1.1 is the distance time graph for the car from t equals 0. State the property of a distance time graph that corresponds to speed. Remember, that is the gradient, so change in y over change in x. Using figure 1.1, determine the initial speed of the car. So to find the initial speed of the car, we're going to have to draw a tangent at 0, so that's here. I'm going to do it like this. So to find the gradient, it's 60 divided by 2.65 seconds, which is 22.6 meters per second. When the car is decelerating, there is a constant resistive force F on the car due to the brakes. The deceleration of the car is greater than F over m and is not constant. Explain why the deceleration of the car is greater than F over m. So remember, there's that resistive force. M is the mass of the car. So this is actually Newton's second law, force equals mass times acceleration. So explain why the deceleration of the car is greater than F over m. Simply because air friction or air resistance acts on the car to slow it down even further. And why is the deceleration not constant? Because that air resistance changes constantly. Remember, air resistance is all to do with air particles hitting the car and slowing down its motion. Figure 2.1 shows water stored in a reservoir behind a hydroelectric dam. State the form of the energy stored in the water in the reservoir that is used to generate electricity. So notice how high that water is. It's going to be falling, hence it's that gravitational potential energy, which is the energy stored in the water, and then it turns to kinetic energy as it turns the turbine. The turbine is 150 metres below the level of the water in the reservoir. Atmospheric pressure is this, the density of this. Calculate the total pressure in the water at the turbine. So you need to add atmospheric pressure up here to the pressure of the water. So we use this equation, which states that pressure difference is height times density times gravity. So the height is 150 metres. Density, we've been told, is 1,000. Gravity is 10. Put that into your calculator. And then you want to add it to atmospheric pressure. So your final answer is 1.6 times 10 to the 6 pascals. The turbine has a cross-sectional area of 3.5 metres squared. Calculate the force exerted on the turbine by the water. So force is pressure times area. We've just calculated the pressure. It's 1.6 times 10 to the 6 times the area. The answer is 5.6 times 10 to the 6 newtons. The water flows to the turbine through a pipe of constant cross-sectional area. Explain why the kinetic energy of the water in the pipe remains constant as it flows through the pipe. That's all because the speed of the water remains constant and liquids are incompressible, so their density doesn't change. During a picnic on a warm, dry day, a metal can of lemonade is wrapped in a damp cloth. Evaporation cools the water in the cloth. Explain in terms of molecules how evaporation cools the water in the cloth. So remember, those molecules with the highest kinetic energy will evaporate first, meaning that the average temperature of the remaining water molecules is decreased. And lastly, point out that temperature is related to the kinetic energy of molecules. As the water in the cloth cools, so does the lemonade. Explain how electrons transfer thermal energy through the metal of the can. So if you think about the structure of the metal, we've got positive metal ions surrounded by a sea of delocalized electrons. Now, those positive metal ions are vibrating, and they vibrate and therefore collide with the electrons. And then because those electrons are free to move, they'll carry the thermal energy through the metal of the can as they move through the metal. So thermocouples have been removed from the recent specification change, so we're not going to answer this question. Question 5. Figure 5.1 shows a kitchen tap that supplies instant boiling water. Cold water passes over an electric immersion heater inside the tap. The boiling point of water is 100 degrees Celsius. State what is meant by a boiling point. It's the temperature at which a liquid becomes a gas. The immersion heater is powered by the mains at a voltage of 230 volts. When the tap is open, the heater switches on and the current in the heater is 13 amps. Calculate the thermal energy produced by the heater in 60 seconds. We want to use the equation E equals IVT. I is current, so that's 13 amps. Voltage is 230 volts. Time is 60. Put that into your calculator to get 179,400 joules. The specific heat capacity of water is 4,200. The cold water enters the tap is at 22 degrees. Calculate the rate at which water at its boiling point emerges from the tap. What you need to do here is basically find out the mass of water leaving that tap in 60 seconds, even though I don't think the wording of the question makes that particularly clear. So we find the mass first of all using the equation E equals mc delta T. The energy we've just found in the previous part of the question. The mass is what we're after. The specific heat capacity is 4,200. The temperature difference is the difference between the boiling point of water and the cold water. So that's 78 degrees. You want to solve for M to get 0.5476 kg. And then we take that number and divide it by 60 seconds to find the rate at which that water leaves the tap. So that's 9.1 times 10 to the minus 3 kilograms per second. The metal tap is earthed and there is a fuse in the cable that connects the heater to the mains. Explain how the earth protects the user. So if the tap becomes live, what the earth wire does is it provides a connection to the earth, taking that excess charge and current away. And then explain how the fuse protects the circuit. Well, if the current is too high, that fuse wire will melt, breaking the circuit. Figure 6.1 shows a road next to the sea. On a sunny day, the sun warms the road. Describe how energy from the sun reaches the earth and warms the road. So energy from the sun reaches the earth. We're talking about heat energy, so it's going to be infrared radiation. So the sun gives off infrared radiation, which is absorbed by the black surface of the road. The temperature of the road is greater than the temperature of the sea. The surface of the road is black. Suggest one reason why the temperature of the road is greater than that of the sea. Remember, with infrared radiation, the colour is so important. Black is a good absorber of infrared radiation. So remember, if you have black or very dark brown hair, your hair will get very hot in the sun. If you're much fairer, you won't suffer from the same fate. The air above the road is heated by the warm road. Describe how this affects the molecules in the air. Well, those molecules will move faster and gain kinetic energy. Therefore, moving further apart and becoming less dense. A cyclist travelling along the road notices that a cool breeze is blowing from the sea to the land. Explain how convection produces this breeze. You may include a diagram if it helps your answer. So let's start with the road. Here's your road. There's the sea. Gosh, I'm feeling so artistic. Now, that road is hot, so we know that the air expands. The particles move further apart and become less dense. That hot air rises, and as it cools down and becomes more dense, it sinks, setting up a convection current. Figure 7.1 is a full-scale diagram of a small nail in front of a thin converging lens. The line L represents the lens. The focal length of the lens is 3 centimeters. Rays of light parallel to XY are traveling towards the lens. Describe what happens to the light after it passes through the lens. So you need quite an in-depth knowledge of what happens to light rays as they meet a converging lens. First of all, that light will be focused, and as it's a converging lens, it will travel towards a particular point known as the focal point, which is 3 centimeters from that lens. Because look, there's the 3 centimeters. On figure 7.1, mark and label with an F each of the 2 principal focuses of the lens. Use your ruler and measure 3 centimeters from that lens and label each one F. Then it says the small nail N of height 1.2 centimeters is positioned 2 centimeters to the left of the lens. By drawing on figure 7.1, find the position of image I of the nail and add image I to the diagram. So what you have to do here is you start by drawing a diagonal line that goes straight through the middle of that lens. Then you draw a horizontal line off the top of the nail, and then effectively you have to track back because you need these 2 lines here to meet. So starting over here, you track back and draw your line so that it comes through the lens, and that will tell you where the image will appear. So you can see that the image of the nail is going to be virtual because it can't be produced on a screen. It's going to be enlarged and it's going to be upright. So it's virtual because the real rays don't meet. State the name given to a lens. When it is used in this way, it's going to be a magnifying glass. Figure 8.1 shows 2 vertical cylindrical tubes and a cylindrical magnet all held in a vacuum. One tube is made of plastic and the other tube is made of copper. The two cylindrical tubes have identical dimensions. The magnetic field of the small cylindrical magnet is extremely strong. Initially, the magnet is at the top of the plastic tube. The magnet is released and it falls through the plastic tube without experiencing a resistive force. The magnet takes 0.67 seconds to fall to the lower end of the plastic tube. The mass of the magnet is 0.012 kg. Calculate the kinetic energy of the magnet when it reaches the lower end of the plastic tube. So here's the equation you want to use. We've got the mass, which is 0.012, but we don't have that speed squared. But remember, acceleration equals change in speed over time. Acceleration due to gravity is 10 meters per second. The magnet is at rest, which means that initial speed is 0. We're after the final speed. The time we've been told is 0.67. So to find the speed, it's 10 times 0.67. It's 6.7. So now you're ready to put that into your calculator. 0.27 joules is our answer. The magnet is then held at the top of the copper tube and released. As it falls through the copper tube, an electric current is generated in the copper. Explain why there is a current in the copper. And that's because it's all to do with electromagnetic induction. The magnetic field lines cut the copper tube and the electromagnetic force is induced. The current in the copper produces a magnetic field of its own in the tube. The magnet falls much more slowly in the copper tube than in the plastic tube. Explain why the magnet falls more slowly in the copper tube. In this case, there's an opposing force on the magnet, and because that force is linked with motion, then clearly that motion is going to slow of the magnet. So I've just skipped past a logic question because that's no longer on the specification. Two of the isotopes of hydrogen are hydrogen 2 and hydrogen 3. State one similarity in the composition of their nuclei. Remember that the nuclei contains protons and neutrons, so we can see both contain one proton. Describe how a nucleus of hydrogen 3 differs from a nucleus of hydrogen 2. The main difference is that hydrogen 3 contains one extra neutron. To get the second mark, simply point out that there are different numbers of neutrons in the two isotopes. In a nuclear fusion reactor, a nucleus of hydrogen 2 fuses with a nucleus of hydrogen 3 at extremely high temperature. This fusion reaction produces an isotope of element X and releases a neutron. Explain why an extremely high temperature is needed when forcing these two nuclei together. So we've just said that the nuclei contain both protons and neutrons. The neutrons are kind of irrelevant because they have no charge, they're neutral, but the protons will have a positive charge. Now these two nuclei will therefore naturally want to repel each other, and so you need a very high temperature to create the high kinetic energy needed to overcome that repulsion force. So two nuclei are positively charged and therefore repel. Very high temperatures are needed to create high energy, high kinetic energy needed to overcome the repulsion. Using nuclide notation, complete the equation for this reaction. So we've been told that it releases a neutron, so let's draw a neutron here. So remember, a neutron has a mass of 1. It has no atomic number because remember that relates to the number of protons. And then just look at what we have left. We have to make sure the left and right hand sides add up. So there's 5 as the mass number here. We have 1 here, which means we need a 4 there. We have 0 down here for the atomic number. 1 plus 1 down here is 2. Use your periodic table to identify the element with 2 protons with an atomic number of 2, and it is helium.